Today we're in Chapter 7. We're going to be talking about uniform convergence. It's a really interesting idea. It's basically, the big idea of it is instead of talking about sequences converging to x, we're going to be talking about functions converging to another function. So the big idea is instead of thinking about one point, we're going to think about lots of points, and we're going to find that there's an intuitive way we might define this, and that way is actually not the best way. So what would be the intuitive way that you should define Fn going to x? Well, that would be pointwise convergence. So what would it mean to pointwise convergence? We would say if for each x in some domain, Fn of x approaches f of x, then we would say that Fn approaches f pointwise. So what's the idea here? The idea here is we're just looking at each x value and asking ourselves, at that x value, what happens to our point of convergence? So it turns out that this ends up being a little bit of a problem, and let me just give you two examples of this. So one example is going to be the function Fn of x defined by 1 over n times x on the interval 0 to 1. Okay, so what's going to happen to this function? Well, notice that for each x value, the sequence 1 over n to the x, that converges to 0, doesn't it? So for each x value, 1 over n to the x converges to 0 because once you pick an x, that x is constant. And so therefore, Fn to Fn of x should converge to the function 0 on 0 to 1. But notice this is kind of a weird pattern. By the way, I could start drawing these. Let's start drawing them. 1 over x just looks like this. So that'll be 1 over x. 1 over 2x is going to be the same thing, but just a little bit smaller. So 1 over 2x. So wow, I'm really struggling with my ability to draw smooth lines. Let's try again. So 1 over x might be something like this. 1 over 2x is basically all the values, but just half as large. So that's like 1 over 2x. And then 1 over 3x is all the values, but a third as large. And then what we see is that these values are looking like this and this. But what's going on over here? Well, what's going on is here we still have that vertical asymptote. So each function is still unbounded. Right? Because it doesn't matter how big you choose, 1 over 2,000 to x, it's still unbounded. However, the sequence itself is converging to the sequence 0 on 0 to 1. So every single point, whichever point you choose, that single point is going to converge to 0. But the whole function, so the whole function converges to y equals 0. But this feels a little awkward because what we see is that we have a bunch of unbounded points, unbounded functions, converging to a bounded function. And it feels like maybe this, so it feels like maybe this is a little awkward, right? Because you kind of hope that some properties that are true for these Fn functions should also be true for what happens when you take the limit. But notice in this case, that's not true. Okay, let's look at my second example. My second example is the function Fn of x equal to the square root of x squared plus 1 over n. Okay, so Fn of x is the square root of x squared plus 1 over n. If you're playing along at home, this function ends up being like the top half of a hyperbola. So if x equals 1, it's the hyperbola, and they're always the hyperbolas that converge to the line y equals x. And so the first one is a hyperbola that looks something like this. The second one, we move the hyperbola down a little bit, and it converges something like this. And then we move the hyperbola down a little bit. And so that this 1 over n is basically telling us the starting point for our hyperbola. Notice if you put at the 1 over the square root of n, right? So it looks like that. Maybe I should have made that an n squared. Then it would come out really nice. Okay, but we see that what we've got is we've got just a bunch of hyperbolas, each converging to these values here. Okay, but the question is, what happens to the limit of these? Well, notice for each x, the sequence, the square root of x squared plus 1 over n, well, this x is just a constant, and 1 over n we know converges to 0, so this is just going to converge to the square root of x squared, but we all know the square root of x squared is the absolute value of x. So in the long term, this converges to this absolute value function right here. Oh, I guess I should have given us a domain, so I guess we can just do all real numbers because this is convergent for all real numbers. Now, what's interesting about this is what do we notice about each fn? Each fn is differentiable at every point, but in particular at x equals 0. But what do we know about absolute value of x? Absolute value of x is not differentiable at x equals 0. So I took these hyperbolas and I made them converge pointwise, and pointwise they converged to this absolute value function. So what I had is a point here at 0 where there's always a derivative. In fact, the derivative's always 0, but then by the time I converge, it's no longer 0. It does not exist. Okay, so this should bother us too, because we would hope that if we have some sort of convergence of functions, something like the function having a derivative, you would hope that the function it converges to also has a derivative. If you're interested, 7.3 to 7.6 have a lot more interesting examples. They're examples of functions where each of the fn's are continuous, but it converges to something that's not continuous. Each of the fn's are integrable, but it converges to something that's not integrable. But what I want you to do, before you look at 7.3 to 7.6, I want you to work on today's task. Actually, I think there's going to be 2 tasks, but let's work on today's first task. I want you to create 3 of your own sequences. So create 3 of your own sequences, fn converging to f. And they can be anything you want, but I would encourage you to try to be as creative as possible. And you make sure to include the domain. I forgot that last one. Make sure to include the domain. But try to make them as interesting as possible, and see if you can achieve some of these tasks. See if you can make sure that each of the fn's are continuous, but f is not. Or try to do one like I just did, where each fn is differentiable, but f is not. Or try to do one where each f is integrable, but f is not. Or maybe you have some other interesting thing that's different between fn and f. So see if you can make make your sequences and see if you can do those things. Okay, so it's pretty clear that from these examples that pointwise convergence is not the way to go. So we need a better way of defining convergence if we're going to do anything with it. And the answer is uniform convergence. This sounds like uniform continuity, and that's because the definition is quite similar. So let's look at our definition. Our definition looks like this. Fn is uniform Fn converges to f uniformly on some set E if for all epsilon greater than 0, if for all epsilon greater than 0, there exists a capital N such that n greater than capital N implies that fn of x minus f of x is less than epsilon for all x in my set. So what's the difference? The difference is pointwise convergence, we picked x first, so similar to continuity. Pointwise convergence, you pick the x and then you make it converge at that x point. Uniform convergence, you have to make it converge for all x simultaneously. So what's the difference? The difference, let's take for example that first example I had, where we had those functions converging to 0. Well, what's going on there? Well, what's going on there is we have our convergence function f, but you'll notice that even if I take a really large n value, f of some really large n value, it may be really close to f through most of the region, but eventually it's going to spike back up. So notice that there are always going to be values. There are always going to be values here, right? There are always going to be values that are not close to f, and it doesn't matter. How big you choose n to be. There's always going to be this little spike that happens on this left-hand side that makes the values close to f. So point-wise, but point-wise, each of those points, once I pick that point will eventually converge down to f. But that just means that the spike got moved closer to the origin. It didn't get rid of the spike altogether. So what's the difference? Uniform convergence has kind of a picture that we often think about. And the picture might look something like this. We'll have our function f. And then what I'm going to do is I'm going to put just a little, I'm going to have some sort of epsilon. And that means that at each f value, there is some sort of like epsilon window. It's like we made a little tube going around this where each one of these are epsilon from the top and the bottom. And now my function, my f capital N function, whatever it is, it must stay between these green lines. So that's my f capital N function. So what you see is that every point in my sequence, it eventually goes inside that little tube. So it's uniformly convergent. So the whole function is converging simultaneously instead of each point converging one point at a time. Okay, again, this should make you think a little bit of uniform continuity. Instead, uniform continuity meant that we try to pick one delta value that works for the entire domain instead of picking a different delta value for each point in the domain. Here, we're picking one epsilon value that makes the function converge on the entire domain, or we're picking one capital N value that makes that function converge on the entire domain instead of picking separate n values for each point on the domain. All right, so what we're going to do is we're going to prove that some of these properties that are super important are going to be true as long as our function converges uniformly. So here's the big idea for this one. We're going to try to prove that if it converges uniformly, then if if each of the fn's are continuous, then our f is continuous also. So that means that you can't take a sequence of continuous functions and get something that's not continuous, as long as you're converging uniformly. We saw, and you all can work with some examples to see if you can make things that are pointwise that fail at this. Okay, so let's work on this one. How are we going to do this? Well, the answer is, let's just think about what our goal is. Our goal is to show that f is continuous at x naught, and that means that we want to know that if x minus x naught is less than delta, then f of x minus f of x naught is less than epsilon. So that's what we want. What we're going to have to do is we're going to have to make a couple comparisons along the way. So what I know is I know that I can find some sort of n value. I can find some sort of n value such that these f's and my fn's are always close to each other. So I can find an n value such that f capital N of x and little f of x are really close, right, is really small. So less than some epsilon. So I can take my function here, the limit of these things, and compare it to some capital N. But I also know that this is also true for the x naught point. And that's what's nice about my uniform convergence, is that I can pick a capital N value that makes both of these statements true at the same time. So it makes n really, it makes fn of x really close to f of x and fn of x naught really close to f of x naught. So it'll make these things true at the same time. And then finally, I know that since fn is continuous, I can make my fn at x and my fn at x naught less than epsilon. And now if you look closely, you'll see I've actually got like two, or actually got like a triangle inequality with three things connected here. So I'm connecting this one and this one, this one and this one and this one and this one. So I can string these together and combine them. So you might guess that we're not going to use epsilons over here. We're going to use epsilons over 3 because we're going to end up adding all of these pieces together. Okay, let's clear this out. Let's write this proof out nice, because I've gotten in a bad habit of not writing things out nicely. Okay, so what we're going to do is we're going to let epsilon be greater than 0. Then what I know is that there exists a capital N such that for all x in E, fn of x minus, there's capital N such that for all x in E, if n is greater than or equal to capital N, then fn of x minus f of x is less than epsilon. In particular, this means that, let's come back and we'll say that in just a moment. In particular, this means that if I choose x naught or x for my proof, then we're going to be in really good shape. Okay? So now what I'm going to say is I'm going to say, well, since fn, this is since fn approaches f uniformly. Okay? Now, since fn is continuous, and let's just do, since fn is continuous, let's put the capital N on here. There exists some sort of delta such that if x minus x naught is less than delta, then f of x minus f of x naught is less than, and once again we'll do epsilon over 3. Oh, I forgot to put the divided by 3. I think I said it. Since it's continuous at x naught. Okay, so since f capital N of x naught, these should be capital N's here. Okay, so now we're ready to finish our proof. So therefore, we just have to take capital, or little f at x minus little f at x naught. Let's just say, I was trying not to be sloppy, and now I'm being sloppy. Therefore, if x minus x naught is less than delta, we get the following. We get that f of x minus f of x naught is equal to, and now I've just got to go like add my x n's in here the way I want them. So I'm going to do f of x minus f capital N at x, because I want to compare my f to my capital N using uniform continuity. But now I've got to add that f capital N back in, but I'm going to subtract out. But now I'm going to use capital N at x is close to capital N at x naught. And then I'll go plus f capital N at x naught minus f at x naught. So what I did was I added in a capital N at x and subtracted a capital N at x, and added in a capital N at x naught and subtracted an x in x naught. And what I'm really doing is I'm using these comparisons that we kind of laid out at the very beginning. And so this is less than or equal to f of x minus f capital N at x plus f capital N at x minus f capital N at x naught plus f capital N at x naught minus f capital minus f at x naught. And then this is now less than epsilon over 3. That one by uniform continuity, plus epsilon over 3. That one by the fact that fn is continuous, plus epsilon over 3, again, by uniform continuity, because it works for every point. It also works for x naught, which is equal to epsilon. So now I've proven my theorem. Okay, so I wrote that one out nice. This is probably the only one I'm going to write out nicely today. But I write this out nice because I think this is the type of proof that I think's of kind of the level that we give for homework or things like that. So hopefully you could put together a proof like this for homework. The other ones we're going to do, they're not too bad. In fact, the second one is maybe kind of similar to a homework type level proof. So now let's move on to integration. And so we're going to show that if Fn approaches S uniformly, if it converges uniformly to f, and each Fn is integrable, then the function that comes out is integrable. And not only that, but you can take the limit of the integrals and come up with the integral of the limit in a sense. So in some ways, this theorem lets you switch the limit sign. Notice that what's buried inside of here is that this is the limit as n goes to infinity of Fn. So it's like it allows you to switch the limit and the integral sign. Okay, but let's tackle this problem and look at it. And the way we're going to do this is we're going to start by using the fact that it's uniformly continuous to get Fn and f really close to each other. And then we're going to look at the function f minus Fn. We're going to look at the function f minus Fn, and we're going to see that that function has to be 0. And then once we see that that function has to be 0, then our upper, less than epsilon, and then we'll use that function is close to each other to get that the upper and the lower estimates for f have to be really close to each other. Okay, so that's kind of at the heart of what we're going to try to do. So let's start out with this. So let's not go quite into the same detail that we did last time, but of course we'll start with an epsilon greater than 0. And then what we'll do is, because it's uniformly continuous, we know that there exists some capital N, such that if n is greater than or equal to capital N, f of x minus f n of x is less than, and I already know what the end line is going to be, so I'm going to go ahead and write it out, epsilon over 3 b minus a. The 3 comes from kind of a similar estimate that we did on the last, and then b minus a is the length of the interval, and that's because as we start adding these together, we're going to get an interval together. Okay, so now that we have this, all we have to ask is, what is the upper estimate for f minus fn? So what's the upper estimate for all of these f minus fn terms over any partition? And notice that all it is the sum of the maximum values on the partition, and I'll just put a j, times the width of the partitions. But notice that each of those maximum values has to be less than this estimate that we made a second ago, because that's what uniform convergence tells me. So that means that this has to be less than epsilon over 3b minus a times the sum of the delta xj's. Oh, this should have been an xj. And then what is the sum of all these xj's? Well, this is just b minus a. So my upper is, so my upper estimate for f minus fn is less than epsilon over 3, because I get that this term here was b minus a, and it canceled with that b minus a. Similarly, I can get that my lower estimate for f minus fn for any, and notice this is true for any partition, it doesn't matter which partition you choose, that has to be greater than negative epsilon over 3. So that upper and that lower have that epsilon over 3 connection. Okay, but now the next thing that I know is fn is integrable. And so what does that mean if fn is integrable? Well, fn is integrable means that there exists some partition, P, such that the upper of that partition, and I'll use capital N here, so f capital N is integrable. So we're talking at this first one that makes epsilon bigger than that. So it means that f capital N P minus the lower f capital N P is less than epsilon, but in this case we're going to also make that epsilon over 3. That's just what integrable means, right? So the definition of integral means you can take your lower and your upper sums, and the difference of them can be made as small as possible. Okay, so that's my result. And now that I have all of those, I'm ready to show that my capital F has to be integrable. So the way I'm going to do that is I'm going to compare my upper and my lower for capital F. So let me get some space to write here. Maybe I'll write at the very bottom. Okay, so the way I'm going to do that is I'm going to compare my upper and my lower for f. So this is the limit of the function. This is the upper and lower sum of this function, the limit of them. And I'm going to use the upper and lower for my n from my sequence. And then I'm going to use uniform continuity to make a connection between those. So my upper minus my lower, well, this has to be less than or equal to u of f minus f capital N for my partition plus u of f capital N of my partition minus L of f capital N of my partition minus L of f minus f capital N for my partition. And then what you see here is so what's going on? Well, what we're saying is that this subtraction, I'm not sure how it breaks out, but it breaks out so that it's this plus this. So here we see we've got the minus the capital Fn and the plus the capital Fn over here, and those in an estimate work out to be bigger than this Fn itself. Okay. So they have to be bigger because if the capital F, if the F and the Fn's are positive, then these would actually cancel each other out. But if you get some sort of positive negative situation where pieces are adding to each other, then this might potentially have gotten bigger on the right-hand side than on the left-hand side. But at any rate, this UFN minus there is less than that. And now let's look at these estimates. Well, what I know is that this is less than epsilon over 3. And then these two right here, these two middle terms, are less than epsilon over 3. And then minus this was bigger than negative epsilon over 3, so that's bigger than epsilon over 3. So when I add them all together, I get that it's less than epsilon. So this shows that f must be integrable because I was able to take the u and l's and connect them. Notice I'm actually doing something very similar to what I did before, right? So when we did continuity, we had to make a connection from the specific point to a nearby point, and then had to make the connection from the function to the functions in the sequence using uniform continuity. We're kind of doing the same thing here. We're making a connection from the function to the functions in the sequence using uniform continuity, and then making the connection between the upper and lower sums using using what we know about the partition to make this all happen. Okay, so this is great. So we know that our function is integrable. So let me clear this. So we know f is integrable. And what does that mean? Well, that means that we can find the integral of it. And so that means instead of taking the limit, we can either take the limit of each integral separately, or we can take the limit of the function first and then take the integral second. So it doesn't matter which one you do first, you get the same result. Okay, so that's that. Now it's time to talk about differentiation, and I'm going to skirt some of the details of the proof on this one just because I feel like you guys are getting a little tired of these long, painful proofs, but and I am as well. But I will tell you at the heart of kind of what we're going to do to prove this. But so the question is, if fn is a sequence of differentiable functions such that fn converges uniformly to f, and these differentiable functions, the derivatives, converge uniformly, then what we're going to say is that the derivatives of those functions, the limit of them, is actually the derivative of the function that you've got. So f is differentiable in every point. So this means that original example I gave where where each of my fn functions had a derivative, but the limit didn't have a derivative, that's not possible if we have uniform continuity or uniform convergence on the sequences and uniform convergence on the derivatives. That's not going to work for these. Okay, so uniform convergence is what's going to make this happen. But what I'm going to do is I'll just kind of quickly introduce you to the proof. And the big idea of the proof is that we have our function fn, and we're going to compare that function to another function gn. And gn is written piecewise, and we're going to write it as fn of x minus fn of c divided by x minus c. And this is if x is not equal to c. And then we're going to make it fn prime of c if x is equal to c. And then the most important thing to notice here is that gn is basically defined to be the difference quotient, so that derivative equation, if it's not equal to c, and then it's the actual derivative at c. So what we see is that because fn is continuous, or fn is differentiable, what we end up getting is that gn is continuous. So these gn functions are continuous, so that means gn has to converge to some function g, and that g function itself is also continuous by what we had earlier. And then all that's left in the proof is to make a connection to notice that, well, what is gn approaching to? Well, the gn is approaching g, and that g has to equal, and that g of c has to equal f prime at c. So we kind of get, we use, instead of using the f's to make the continuity, we use these g's, and these g's must be continuous, and they're uniform, and they converge uniformly. So we can use that previous theorem on continuity to make a bridge between these g functions and our f functions we want. So that means f prime has to be differentiable at that point, and that f prime of c is equal to whatever the limit of these f prime of n of c's are. Okay, so I left out all the details. The details kind of go through why we're allowed to make these connections and what's going on with all these things. But I thought you all could live without the details. So go read the textbook. This is the last proof in chapter 7.1, theorem 7.12, and I think you will enjoy that. Okay, just a little bit of a glimpse as to why do we care about this. Well, we do care about functions converging to each other, but there's one set of functions that we care about a lot more than the others. And so you all know we've written before that we might write a function like e to the x as the sum as k goes from 0 to infinity of x to the k over k factorial. So you've probably seen this formula before. This is the Taylor series, or the power series of e to the x. And so this is something we did in calculus class, but the question you should be asking as an analysis student is, well, what is this? Well, what this is really, if we define a bunch of functions fn as a series as k goes from 0 to n of x to the k over k factorial, then we have a sequence where our fn's of x's are approaching our f of x. They're converging to our f of x equals e to the x. But now you can see what we really want is we really want to be able to ask questions like this. Can I just take derivatives of these, and is that the same as taking derivatives of e to the x? Can I take integrals of these, and is that the same as taking integrals of e to the x? And if these are always continuous, does that mean e to the x is continuous? So you see how we want to ask these questions about our function in terms of the power series of the function. And so we've seen from this section that what we really are asking, and we have one question that we need to establish, and that is this power series uniformly convergent? That is, do these f's converge, fn's converge to f uniformly, or do they converge pointwise, because once they converge uniformly, then we have all the different things that we want from it, right? We have differentiation, we have integration, we have continuity, but we only know that if it's uniformly convergent. So I'm going to come back in a second video in just a minute, and the main goal is going to be tackle that question of, do these power series have to converge uniformly, and then once they converge uniformly, what can we